Development team here at NREL. The topic for today's webinar is to present the results of a recent project by the SAM team to validate the flat plate photovoltaic performance model in SAM, which has been a big effort of ours over the last several months. The webinar will be about 40 minutes, with 20 minutes or so for Q&A at the end. And this webinar is also being recorded, and the recording as well as a copy of the slides will be available on the SAM Learning page. This presentation summarizes an in-depth report which was just released yesterday about this validation effort. There will be a link to the full report at the end of this presentation, and it can also be found on the SAM website under Resources, Case Studies, and Validation. The report provides detailed validation of the SAM flat plate photovoltaic performance model by comparing SAM modeled PV system generation data to actual measured production data for 9 PV systems ranging from 75 kilowatts to greater than 25 megawatts in size. The results show strong agreement between SAM predictions and field data, with annual error below 3% after known causes of error were removed. The analysis identifies 2 known causes of error, snow cover, and an incorrect implementation of the backtracking algorithm in SAM. It also identifies a seasonal variation in monthly error and concludes that for these 9 systems, there is no increase in error with an increase in system size. Before getting into the validation project itself, I just want to mention that this webinar is part of the 2013 to 2014 SAM webinar series, which you can see listed here. This schedule can also be found on the SAM Learning page, and from there you can register for any of these free 1-hour webinars. If you can't make a webinar that you're interested in, don't worry. We also plan to record and post all of the webinars after they're given so that you can listen at your convenience. But we encourage attending them if you're able so that you can ask any questions you might have. In today's presentation, I'll go through the entire process of this validation report, including the reasons that we undertook the project, the methodology we employed to complete it, and our various findings and conclusions. There will be time for questions at the end, but if you have questions during the presentation, please type them into the chat window and we will answer them as time allows. To begin with, I'd like to introduce you to the motivation behind this validation project. What is validation, and why should we go through the extensive effort to validate the SAM PV performance model? As most of you know, there are a plethora of models available in SAM. In order to run a simulation, you must choose both a technology performance model and a financial model. The performance models include technologies from solar to wind to geothermal, and the financial models represent residential, commercial, or multiple types of complex utility-scale financing options. This validation project focuses only on the flat plate photovoltaic performance model, whose key output of interest is hourly energy production. Let me also clarify what's included in the SAM PV performance model versus the financial model. The performance model takes as inputs the weather data for the project location and the system specifications. First, it runs the weather data through a radiation transposition algorithm to predict the radiation in the plane of the photovoltaic array. Second, it applies a PV module model to predict the DC power produced by the system. Third, the DC power is then fed into the inverter model, which predicts the AC power produced by the system. Losses are also applied as appropriate throughout this process. At this point, the performance model portion of SAM is complete, and the AC power is fed into the financial models in order to predict the financial metrics associated with the system. As a side note, we are also currently working on a PV reference manual, which walks through these side steps in much more detail to fully describe the PV performance model. So now that I've clarified what we're validating, that begs 2 questions. How and why are we validating the PV performance model? The how part is easy. In this case, we're validating the performance model by comparing the energy output predicted by SAM to the measured output of real operating systems. This helps us to verify that it is appropriate to use SAM to predict the performance of systems that have yet to be built. The why is a little more in-depth. Validating a performance model is important for a few reasons. Firstly, performing a validation study allows us to identify any particular areas that might need better algorithms or further model development. Secondly, we're also responding to requests for this type of model validation. But lastly, while various validation studies have been conducted at the component level, for example, the module performance models or the inverter performance models, current tools such as SAM are not sufficiently validated across a broad range of systems to establish confidence in the accuracy of these models compared to the performance of an installed system. Validating the PV model allows us to give SAM users more information about how the model performs, which can provide a better understanding of the capabilities and also the limitations of the model. This in turn can translate to higher confidence in the model, which can reduce risk and allow the industry to make intelligent investment decisions surrounding photovoltaic projects. Now that we've established why validating the performance model is important, I'll briefly explain the methodology used in this validation study. We go into the methodology in much more detail in the full validation report, but a quick overview is helpful to understand the applicability of the results that we obtained. For this validation study, we performed a detailed analysis of 9 systems, shown in the table here, in order to quantify SAM's ability to predict the performance of those systems. These systems were chosen based on our ability to obtain detailed measured data and specifications about the system. 7 of the systems were fixed tilt systems, and 2 were one-axis tracking, and they range from thin film to crystalline silicon panels. Their geographic spread encompasses Washington, D.C., Florida, the desert Southwest, and here at NREL in Colorado. They include 6 commercial scale systems that range from 75 to 700 kilowatts, and 3 utility scale systems that are 10 megawatts or greater. Note that for the purposes of this study, we define commercial and utility scale as a range of sizes instead of a financing option. It's important to examine both commercial and utility scale systems because there are some utility scale phenomena that we do not explicitly model in SAM, such as spatial resource and temperature variability, staged inverters, etc. Data collection is a very important component of a validation effort. In order for us to determine how well SAM can predict the performance of real systems, we need as accurate of system specifications as we can get so that we can tell SAM to model the proper thing and not mask modeling error with errors in specification selection. For the majority of the systems in this study, we knew the model, quantity, and arrangement of the modules and inverters in the system, as well as the exact tilt angles and geographic locations. For the 2 First Solar utility scale systems, the exact layout of the panels was not known, so we sized them automatically in SAM, given the nameplate AC capacity and the default AC to DC ratio assumption of 1.1. The weather file input for validation simulations is also incredibly important. Many SAM users will use a typical meteorological year file as their weather file to input to run SAM. When that is the case, the energy production values are the prediction of a typical year, not necessarily a real year of production. In the case of the validation study, however, we wanted to separate weather data uncertainty from model error. Therefore, the weather data used as an input to SAM was the concurrent data with the measured performance data, and it was as high of quality as possible. For the systems located here at NREL, we were fortunate to be able to use high-quality measured irradiation and weather data from the Solar Radiation Research Laboratory shown here. The Forestall system in Washington, D.C. also had high-quality measured irradiation and weather data on site that was used as a weather file input into SAM. For the 3 utility scale systems, only global horizontal irradiance measurements were available on site, so we used concurrent satellite modeled weather data for the remainder of the necessary weather components at those sites. Once we had all of these data pieces for input, we ran the systems through a SAM simulation and took the gross AC output to compare to the measured production data, which were all measured at the inverter output. Another large part of the validation effort is the data quality control of the measured data. Real-world measured data frequently contains data quality issues, and real-world systems sometimes experience planned or unplanned shutdowns or component failures. However, the purpose of this validation study was to compare SAM modeled data to accurately reported measured performance data from a correctly operating system. Therefore, missing, interpolated, and estimated measured values had to be removed from the analysis, as well as data taken when sensors were operating incorrectly or when the system was experiencing some type of outage or shutdown. The figure here shows one example of the extensive data quality control process that was a part of this validation. The plot shows the data streams of 5 separate pyronometers at one of the utility scale sites measuring on-site global horizontal irradiance. And you can see multiple data quality issues present in this 2-week span, which include missing data, interpolated data, unrealistic data such as measurements at nighttime, and spikes in the data above the threshold of possible irradiance values. The other largest quality control piece was to identify system shutdowns and inverter outages. Note that removing these values meant removing the entire hour in which they occurred from both the measured and the predicted data sets. Finally, prior to computing any results, we removed nighttime hours from the analysis. We are interested specifically in the daytime hourly error because that is when the performance model runs. The only production predicted by SAM at night is a small negative value equal to inverter operating losses, which are not a part of the overall PV performance model, but rather are calculated directly from inverter specifications. Therefore, including the nighttime hours would skew hourly statistics to indicate a lower error than the error of interest. So we removed nighttime hours in order to avoid presenting misleading statistics. As I mentioned, one of the 2 biggest reasons to perform this validation study was to identify areas of the SAM algorithm that might need improvement or further research and development. During the course of this study, we were able to isolate and identify 2 separate causes of error that had large effects on SAM's ability to predict power production. While not accounting for all system error, these 2 known causes of error did cause significant prediction errors, so I'd like to go into them quickly now. The first known cause of error that resulted in significant disagreement with measured data is snow cover. This is a recognized issue, but has not been fully quantified, nor has a robust method been developed to predict losses due to snow. As you can see from this time series plot of SAM predicted power in red, measured power in black, and measured snow depth in purple, snow can cause huge and inconsistent discrepancies in an otherwise fairly accurate model, if not properly accounted for. Of the 9 systems in this validation study, 6 are located in snowy climates, and uncorrected snow cover increased the total monthly error of those systems up to 350% in the worst case. Fortunately, data affected by snow cover can be removed from a backwards-looking validation study fairly easily by using nearby measured historical snow depth data. Therefore, all of the results presented in this webinar were calculated after the data was processed to remove any hours affected by snow cover, because this known cause of error has already been identified and quantified for this study, and it could possibly mask other model errors. The remaining problem with snow cover issue is how to model it predictively. Unlike a backward-looking validation study, this is incredibly difficult in a forward-looking predictive simulation, since to do it perfectly you would need to know on what days it will snow, how much it will snow, and how the snow will stick to the panels, which varies between snowstorms even for the same system, depending on local conditions at the time of the storm, including temperature and relative humidity. A few models have been developed to begin to calculate a monthly loss due to snow, including one that's in progress here at NREL, which can be input as a monthly soiling loss into SAM. However, these models require appropriate typical snow depth data, which is not as easy to obtain as typical irradiance data. Additionally, these models require the average number of snow events in addition to the average snow depth, which can vary greatly from year to year. These difficulties in predicting an appropriate snow loss mean that existing models have yet to gain large-scale acceptance. However, we recognize the need to address the extreme impact snow can have on a PV system, and implementing such an algorithm is on our SAM development wish list, particularly as the cost of PV decreases and PV penetration increases in markets where snow cover is an issue. The second known cause of error that we discovered in this validation study was a backtracking implementation issue. Up to the January version of SAM, the implementation of the backtracking algorithm in SAM was incorrect for one-axis tracking systems with backtracking capabilities. This was first revealed by studying the scatter plot on the left. In this figure, hourly SAM predicted power production is plotted on the y-axis against the same hour's measured power production on the x-axis. If SAM were to perfectly predict measured data, all of the points on this plot would fall on the one-to-one line shown in black. However, as you can see, there is a large spread above the one-to-one line in the plot on the left. To further isolate the cause of this spread, we grouped the points by their corresponding solar zenith angle, where the high zenith angles shown in red and yellow occur nearer to dawn and dusk, and the lower zenith angles in purple are in the middle of the day. The dawn and dusk hours are when backtracking is in effect, and further investigation of this problem revealed that there was an error in SAM's backtracking algorithm, where for hours that should have been experiencing backtracking, SAM was in fact setting the tracker rotation angle to its maximum. Since SAM was correctly disabling row-to-row shading when backtracking was enabled, this resulted in unusually high overprediction for these hours. Fortunately, this error was a relatively easy fix that was addressed in this September's version of SAM, resulting in much better agreement for one-axis tracking systems, as shown in the scatter plot on the right, which shows the same data as the plot on the left, but using the September version of SAM. However, since the version of SAM being validated in this study was the January version, the two one-axis tracking systems, Mesotop and DeSoto, still contain this known source of error. Data for the DeSoto system are not as affected by the backtracking issue as Mesotop due to the larger row spacing in the DeSoto system. However, the results of both systems are excluded from aggregated results because we were unable to remove the known source of error while still using the January version. Annual error results obtained with the September version, which utilizes a corrected implementation of the backtracking algorithm, are also presented for these two systems, but those results are not aggregated with the results from other systems. After we identified and removed these two known causes of error, we began calculating various error metrics for the 9 systems studied. Since SAM users may care about accuracy on a range of timescales from an annual basis down to an hourly basis, we examined error at multiple time resolutions, and I will show all of those results here. The first metric that we examined was the annual error of SAM predictions, which was computed as the difference between measured and SAM predicted annual energy production values, normalized by the measured annual energy production. By this definition, a positive error indicates that SAM overpredicted the system's power production. This plot shows the normalized annual error for each system. When multiple years of data were available for a system, each year's error is shown in gray, and the average annual error for the system is shown by the green circle. Excluding the Mesotop and DeSoto systems, which still contain the known backtracking issue in the January version of SAM, the annual error for all systems is 3% or less. Additionally, there is no noticeable relationship between the magnitude of annual error and the size of the system, despite the fact that SAM does not explicitly model some utility scale phenomena. It's interesting to note that SAM tended to underpredict measured production. Note that all of these values were computed using the default loss assumptions found in SAM, which include a 5% annual soiling loss. This is a potential source of SAM's tendency to underpredict performance. The results of the September version are also shown in this chart for the Mesotop and DeSoto systems, indicated by the green X's. And you can see that using the September version of SAM reduces the error in both systems, more noticeably in the Mesotop system because of its smaller row-to-row spacing. However, the annual error of the Mesotop system remains higher than the rest of the systems at an average of 7.6% even with the new version. Further investigation into this caused us to suspect that our documentation for the Mesotop system may have an incorrect specification. The documentation specified a ground coverage ratio of 0.4, but when we ran SAM with a ground coverage ratio of 0.45, we saw better agreement with measured data. This is discussed in detail in Section 4 of the validation report if you're interested in more information. Next, we examine the monthly error in SAM predicted power production. Monthly error was computed similarly to annual error, where for each month, the difference was taken between SAM predicted monthly energy production and measured monthly energy production, normalized by that month's measured energy production. In the monthly results, an interesting trend is revealed. As you can see in the plot on the left, graphing the error by month results in a convex shape that indicates a seasonal variation in SAM error. For most systems, this variation results in SAM over-predicting power production during the winter months and under-predicting power production during the summer months, even after the data have been corrected for snow cover. Mesotop is excluded from this graph simply to allow us to zoom in more on this seasonal trend, but it is present in the Mesotop system as well. As you can see in the figure on the right, this monthly trend is consistent with findings by Sandia National Laboratory that both of the two popular radiation transposition models, generally regarded to be the most accurate, which are the Perez model and the HDKR model, exhibit the same seasonal variation in error. This suggests that the seasonal error variation may be attributed in whole or in part to the seasonal error of the irradiance transposition models used. Note that these models are not SAM-specific and are used in most, if not all, current PV performance modeling software packages. Other possible contributors to the seasonal trend could include temperature or soiling effects, seasonal irradiance differences, or a combination of factors. We have also conducted a preliminary analysis to see if the difference in SAM error correlates more highly with temperature or rainfall for one system, the DeSoto system. And we observed a much stronger correlation with rainfall than temperature. Rainfall amounts also correlate with this seasonal trend in error at the NREL systems. One potential explanation for this correlation with rainfall could be that the rainfall affects the soiling of the panels, or it could be a secondary correlation with something else. All of these possible causes of seasonal error variation will be explored in future work. Finally, we examined the agreement of SAM predicted power production with measured production on an hourly timescale. The normalized root mean squared error, which is normalized by each system's maximum measured power, is a good indication of overall agreement between SAM predicted power production and measured power production for a given system on an hourly basis. Excluding the Mesotop and DeSoto systems, which as I mentioned still contain the resolved backtracking error, the hourly normalized root mean squared errors for all systems were 5.1% or less. The best hourly normalized root mean squared error was observed in SAM's model of the Forestall system, less than 2%. This demonstrates how high-quality measured weather data and high-quality measured performance data can affect the accuracy of predicting a system in a backwards-looking validation. Again, there is no noticeable relationship between system size and normalized root mean squared error, despite the fact that SAM does not explicitly model some utility scale phenomena. At an hourly timescale, we also examined the normalized mean bias error and 90% confidence intervals. The normalized hourly mean bias error is computed as the average of the hourly errors, SAM minus measured data, subsequently normalized by maximum measured power, and is an indication of SAM's average hourly bias in predicting the power production of a system as compared with measured data. The 90% confidence interval is computed as the percentage error containing 90% of the hourly errors. These statistics are shown here in order of system size, increasing from left to right. Almost all of the examined systems had a normalized hourly mean bias error of less than 1%, the only exceptions being the DeSoto and Mesotop systems, which still contain the known backtracking error. Consistent with annual error, the majority of the systems show slight underpredictions. There is no observable relationship between system size and normalized hourly mean error or confidence interval. The confidence interval is also a good measure of SAM's ability to accurately predict a system's power production, because a small confidence interval indicates agreement for the majority of hours, and unlike mean bias error, shows the spread of errors. Excluding the Mesotop and DeSoto systems, all systems have 90% confidence intervals within plus or minus 8% of measured values on an hourly basis, meaning that 90% of all hourly predictions are within plus or minus 8% of measured values. The Mesotop and DeSoto systems still contain the backtracking error, which contributes to their larger than normal confidence intervals. As I mentioned before, the effect of this error is much larger on the Mesotop system than the DeSoto system, due to its rows being spaced more closely together. The smallest confidence interval observed was the Forrestal system's confidence interval of plus or minus 2%. As I mentioned previously, this is because of the high quality of the measured weather data used as inputs, as well as the high quality of the power measurements of this system. So that just about wraps up the work that we performed for this validation study. And clearly we were left with some future work that we would like to do, such as addressing the issue of snow cover. Additionally, we are following up with 2 projects that continue the validation work. One project is a subcontract to a performance monitoring company to perform a validation across many systems on the order of 100 to capture a better spread of systems rather than an in-depth analysis of each system. Hopefully, you can look forward to the release of that report within the next few months. The second project is for us to expand this validation effort to compare multiple popular PV performance models in order to provide the industry with sufficient confidence in PV modeling in general, not just SAM. Thus far in our validation work, though, we've reached several conclusions. Excluding the Mesotop and DeSoto systems, we found the annual agreement of SAM to be within 3% of measured data, hourly root mean squared error within 5.1%, and hourly mean bias error within 1%. We also noticed a seasonal variation in monthly error, likely the result of a similar trend in the radiation transposition models, as shown by Sandia, that we will investigate further in future work. Finally, we did not observe any increases in any error metrics as the size of the system increased, despite the fact that SAM does not explicitly model some utility scale phenomena. I want to reiterate that these are the results for this backward-looking validation study of the PV model only, using concurrent weather data. These results are not necessarily the error that one should expect when conducting a forward-looking predictive evaluation of a system, since using any type of typical year weather data will result in prediction for a typical production year that is not necessarily in line with any real data set. However, these results can give users an idea of how accurate the PV performance model portion of SAM is when compared to real operating systems. So that's all I have for the webinar today. I have here a link to the full validation report, which is published on NREL's website, and you can also find the full report on the SAM webpage under Resources, Case Studies, and Validation. I'd like to thank you for taking the time to listen today, and remind you that a recording of this webinar and a copy of the slides will be posted on SAM's Learning page if you'd like to share the information found in this webinar with others. We look forward to seeing you in February for our next webinar, Solar Resource Data 101. And we still have some time left for questions, so please feel free to type any other questions you might have into the chat window at this time. Thanks, and have a great rest of your day.
Thanks, Janine. This is Paul Gilman. We do have a couple of questions here, so I'll just read them to you. The first one is regarding the concurrent satellite data that you mentioned. And the question was whether that data is available for SAM users to use on their own.
Yes.
Up through the data is available on a site-by-site and year-by-year basis from our Solar Prospector website, which is at maps.nrel.gov/prospector. And it's available through there through 2010. More recent data is available. NREL licenses more recent data from Clean Power Research for more recent years, so that more recent data is not publicly available at this time.
And I think it's worth also mentioning that was Nate Blair, by the way, the manager of the SAM project. And this is Paul Gilman again. It's worth mentioning that on the download weather file feature in SAM does allow you to measure to download specific year weather files in addition to the typical year files. So it is possible to download specific year weather files for locations in the continental United States. And then there's another question, which is whether you could spend another minute or so describing what the backtracking error was in version 2013.1.15 and earlier.
Sure. Do you want to do it or want me to?
I'm sure I'm happy to do this. This is Aaron Dobos, same team member. So it had to do with the rotation limit. It wasn't being applied in the correct order in the algorithm that was determining what the correct angle was for the backtrack system. So we fixed that, and that resolved the issues at the edge cases where it wasn't working properly.
Thanks, Aaron. There's another question here. Will you be studying effects of soiling in desert area and areas of low rainfall?
This is Nate Blair. That's a really important question. And DOE as a whole has decided soiling is an issue. Our team is not directly working on that. There is research going on at Sandia with regards to soiling currently, and elsewhere at various universities. And I think that if there gets to be a really solid model or a set of data that can represent soiling relatively accurately, we will incorporate that into the SAM model in the future.
Okay, thanks. There's a question here. I noticed that the newest version of SAM does not support installation on Windows XP. Is this going to be the case for all future versions of SAM? I think I know the answer to that one. Yes, we're no longer supporting Windows XP. That's because Microsoft is phasing out support for that operating system. So they won't be issuing updates and so on.
In addition, NREL internal networks don't allow Windows XP, so we can't actually develop the software to run on all those older platforms as well, unfortunately.
And do the testing.
So if there are any other questions out there, please feel free to type them in the chat window. What future work is planned for snow cover?
Right now, we are working with others to look at the algorithms that have been developed to predict some type of monthly snow cover loss, which unfortunately are still under development. And in order for us to implement them predictively, we also need to find reliable sources of snow depth data. But that is something that we are interested in implementing in SAM and hope to have sometime in the near future. So it would end up as some type of monthly soiling loss during the winter months, at least at first.
Okay. And then, did I understand it properly that you first measured weather data and output power of actual installation, and after that you implemented this data to SAM?
Yes, that's correct. We obtained the measured data from other parties, but we used measured weather data to create the weather file that SAM needs to read in order to run a simulation. And then we took the output of SAM and compared it to measured performance data in order to get all of these statistics.
And are there not any clear hydrobolic sprays for snow?
Not that I'm aware of.
And let me just add, this is an A-player, let me just add on that previous question. Another way to go about the validation would be to run the metadata we have about the system against what you would often run, which is more of a typical year file. But we wanted to really look at more at the system models and remove the interannual variability of the weather from this analysis. But obviously the error from a specific year to what SAM would predict off of a typical year would increase the error metrics if you were to do that. And then it becomes very much about which specific year of data you are comparing against and what the weather data varied. And so we didn't really want to look at the interannual weather variability, but we really wanted to look at the system models themselves. And so that's why we chose the validation approach that we did to really hone in on the specific features of the model.
And I'll add that there have been other published papers about uncertainty of weather data separately from the SAM team that can be a good resource for how that uncertainty might additionally affect the error of a simulation.
Okay. If there are any other questions, please feel free to type them in the chat window. Were all systems free of near shading influence?
We actually did have that problem with one system in particular, the Forestall system, that we did not have sufficient metadata about the system to model the near shading. And hopefully in a future version of SAM, we will also have a better 3D shading modeling tool that would allow us to more properly model that system. So what we did in this validation effort was simply to remove those shaded hours for that system.
Okay. I see someone has raised their hand, and now it's not raised anymore. Any other questions? These are great questions. Okay, and as Janine mentioned, we're posting recordings and other related materials for this webinar on the learning page of the SAM website. And that's also where you can find registration information for the remaining 3 webinars in this year's series. Oh, there's another question. Is the SAM team going to look into intra-hour modeling?
This is Aaron Douglas again. Yes, we do intend this year to extend our PV performance models to be able to run sub-hourly. There are a couple related issues with that. One is, of course, having sub-hourly resource data to run those models with. I think that data may exist for certain systems out there, but we don't have a comprehensive sub-hourly irradiance and weather data set for the country. There are algorithms being developed to take hourly data and synthesize sub-hourly data with representative statistics from that hourly data, but that is still in the research phase. The other aspect of sub-hourly modeling that we need to consider is that we need to double-check that for example, the cell temperature models are appropriate for running at sub-hourly time steps. All the models that are currently in SAM were originally designed with 1 hour time steps in mind, and so we just have to ensure that the models make sense for sub-hourly time steps. So anyhow, that is in the general plan for the year coming up.
And add that we get this question a lot with regards to more complex utility rates and 15-minute demand windows and people that are interested in modeling things at sort of the 15-minute level. We don't anticipate going to really anything sub 5 minutes or something like that. We don't, or sub-minute. We don't think that our models in general are appropriate for that kind of analysis at this point.
Okay, have you tried to check the difference in error if you would use TMY weather data instead of measured data?
We did not do that for this study, since we were, as Nate said, trying to really hone in on the model error itself. I believe that there are...
Yeah, so there's a number of studies kind of in the resource assessment literature regarding that. I think that, typically people think of, depending on where you are in the country, something like plus or minus 10% is a decent variable. I would add that one of the capabilities we do have in SAM, which we didn't discuss today, is what we call the P50, P90, or exceedance probabilities capability. So you can run for a particular location all of the 20-plus years of historical data that are available. And we're actually going back. There's some data filling that needs to take place in some of those historical files. We're going back, and we will be re-releasing some of that historical data with updated wind speed and temperature data in particular for both TMY2 and TMY3 type locations. So that's how people typically get at that from a weather data perspective, looking at what does a, quote, bad year, unquote, look like for a particular location, how much less output do you anticipate getting in kind of 90th percentile year. So you can check that capability out in SAM under the advanced features menu.
And I will include a link to some of this research we've been mentioning about, modeling accuracy and typical year data. I'll include links to those documents on the page for this webinar. One other question: do you anticipate someone developing a transposition model that corrects the seasonal variation?
One interesting thing that we saw in the Sandia paper that I cited earlier is that actually the isotropic model does not have this same seasonal variation as the Perez model and the HDKR model, even though the other two are generally regarded to be more accurate. And if you look at the trends of the three transposition models, the isotropic model does in fact have a flat error, but it's consistently too low, whereas the other two have this seasonal error around 0. For future work on the SAM team, we would like to identify where this seasonal bias in SAM comes in, if it is in fact just transposition model or if there's some other effect also happening there. But on our team, I don't think we anticipate doing any type of correction to the transposition models themselves because they're not something that we developed.
I think I will add that we do anticipate doing some additional, having some additional conversations with Sandia, who we work with closely, and evaluating if there are recent improvements in transposition models. As far as we know at this time, no one is working in detail on these kinds of issues. Everyone sort of felt they were resolved some years ago, but I think that you know, our analysis here and the increased attention to detailed variation seasonally is perhaps driving additional improvements in that area. But at this time, we don't have any funding or plans to work on that ourselves.
And just a quick clarification, when we say Sandia, we're talking about Sandia National Laboratories, which is a sister national lab to NREL. All right, I don't see any more questions here. Wait a couple more seconds in case someone is typing.
And just quickly, Paul, what's the next topic for webinars coming up?
The next webinar is Solar Resource Data 101, which will be on February 12th, and Janine will be presenting.
All right. Well, not seeing any other questions. Thanks, everyone, for listening, and we'll hope to see you at the next webinar.
Bye-bye.